Hey guys, how are you today? I know there are many videos out there explaining the difference between virtual machine and containers, but I thought I'll make one more video. So let me get straight into it. Let's first look at virtual machine. What is virtual machine? If you take a normal computer, a computer will have operating system and hardware. Okay, so we'll have hardware at the very bottom. This includes your CPU, disk, and all the IO devices and everything. So we have this hardware, and then we have operating system. Operating system is the one which controls this hardware, right? On top of this operating system, we'll have applications. We may have many applications like app 1, app 2, and so on and so forth. We can have any number of applications. These applications can't talk to hardware directly. So if it wants to read something from the disk, or if it wants to receive a message through a network port, or if it wants to receive a message through a keyboard input, it can't do so directly. It has to go through operating system, because operating system is the boss here. Operating system owns the hardware. No one can talk to or take advantages of the hardware without going through the operating system. So if this application wants to talk to one of the hardware devices, it has to go through operating system. So the way that works is we have something called system call. So we call it syscall. So these syscalls are basically API of operating system to do certain things with the hardwares, right? For example, reading things from the disk or writing to disk. Each of them will have syscalls, and these syscalls can be made by our applications, right? So when I'm talking about the operating system, I'm actually talking about the operating system kernel. So I just want to clarify that, okay? So because operating system itself has two modes, or two type of programs. One is called kernel mode or kernel programs, and the other one is called user mode. Okay, in user mode we'll have some utility libraries and applications, but they don't directly own or control the hardware. They just make it easier to interact with kernel mode. Okay, so when we have applications running on operating system, we usually use these user mode libraries and programs to talk to kernel. So here, when we are talking about operating system, we are just talking about the operating system kernel. Okay, now the problem with this is, because we have this operating system and this operating system owns this hardware completely, what if this hardware is massive? We have massive hardware, like we have 156 cores, and we have many terabytes of memory, but we have this operating system, and on top of this operating system we just run one application, and that application doesn't need all of this hardware. So even if the hardware is not utilized, it can't be used by another operating system, because this entire hardware is owned by this operating system. And this is not a good situation, because if you have on-prem server which has a lot of hardware capacity, but you run one operating system, let's say for Windows, and you also want to have another operating system which is Linux, and you want to take some advantages of the existing hardware, then you can't do that, because both operating system cannot run at the same time by sharing this hardware. So this is where people came up with this clever idea called hypervisor. Okay, so it's called hypervisor. What hypervisor does is, it sits between the operating system and hardware. So if I draw this again, we will have our hardware at the bottom. So this is still going to be our hardware, but there is going to be a thin layer between hardware and operating system called hypervisor. So this is called hypervisor, and on top of this we are going to have our operating system. Okay, and now we can have more than one operating system. So we can have operating system like, let's say this is going to be OS 1, it could be Windows or Linux, and OS 2, and each of these operating system are going to have their own applications, right? So this operating system may have app 1, and this operating system may have app X, app 2 here and app Y here. Okay, so it can have their own operating systems. And here the difference is we have two operating systems running in parallel on the same hardware, but there is going to be this middleman between the operating system and hardware, which routes the calls from operating systems to hardware, and also it allocates fixed limits or fixed amount of hardware capacity to each of this operating system. So if you're talking about RAM, for example, if the machine has 128 gig of RAM, then when we have two operating system running, with the help of hypervisor, we can assign say 64 gig to one operating system and another 64 gig to another operating system, in this case OS2. So these kind of carving can be done using hypervisor. But when it comes to CPU, it will simply do time sharing. Okay, so it will allocate X number of CPU clocks to operating system 1 and then another X CPU clocks to operating system 2. So basically it will do time sharing when it comes to CPU. Okay, so this is the role of hypervisor. Basically it carves out the available hardware to the different operating systems that we are running on top of hypervisor, and CPU, where it can't be allocated directly to a particular operating system, we will do time sharing. So now the advantage is we have this hardware massive capacity within our hardware, and this hardware can be effectively used by two different operating systems. They run in parallel. Okay, so if you imagine that this is Windows and this is Linux, then these two operating systems can share this particular hardware, in the sense that they'll have their own set of memory, and for CPU they'll do time sharing, and this will be facilitated by this hypervisor. So this hypervisor is a very thin layer of program which sits between hardware and the operating system to facilitate the hardware sharing. Okay, so this is what a virtual machine is. And because this whole operating system lives here virtually, as in we call it virtual because we this is not directly sitting on top of a hardware, right? So we have this hypervisor in between. This is why we call this as a virtual machine, and we have two virtual machines here. So depending on our hardware capacity, we can even have many different virtual machines within the same hardware. So this type of hypervisor, which directly runs on hardware, is called type 1 hypervisor, also called as bare metal. Okay, so an example for this type of hypervisor is Hyper-V. So Hyper-V is an example for this type of hypervisor. There is another type of hypervisor which is called type 2. So we have something called type 2 hypervisor. An example for this is VirtualBox. Okay, so the difference is type 1 hypervisor directly sits on top of hardware, right? But type 2 hypervisor is just a software program running on a host operating system. Okay, so I'm just going to draw the same box again, and using that box I'm going to explain how this works. Okay, so we have our hardware at the very bottom. So this is our hardware, and then on top of this we're not going to have bare metal hypervisor. We're just going to have our operating system. So this is called host operating system. So this is basically, again, we're talking about kernel here. Okay, so we have operating system kernel, and on top of this we'll have many applications as normal. So we'll have app 1, app 2, and so on. Okay, so in addition to that, we will also have another let me just make it slightly big because I just want to draw more things on it. So we're going to have another application called VirtualBox. I'm just going to write it as VB. So this is VirtualBox, and this is just another application. You can call it as application 3. But the difference is, within this application, we are going to have another operating system. This is called guest OS. And on top of this guest OS, we are going to have applications running on this guest OS. So let's call it application X, application Y, and so on. If you see this, from the host operating system point of view, we have this big process called VirtualBox. So this is just one process, okay? This is just one process from the host operating system point of view. And within this process, we have guest operating system running. It could be completely different operating system as well. So if host OS is running Windows, guest operating system could be Linux or completely different, okay? So that is possible. And on top of this guest operating system, we are going to have guest operating system's own applications, application X and Y. From host operating system's perspective, these applications are not going to be visible, and host operating system won't even know it is running a guest operating system. From host operating system's point of view, it will just see this VirtualBox as yet another process, yet another application process, just like how it will see the process for application 1 and application 2 and so on. Okay. So this type of hypervisor, so here the VirtualBox is the hypervisor, right? So this type of hypervisor is called type 2 hypervisor, and this is little bit more software heavy than bare metal hypervisor, because every call made by these applications somehow need to reach the hardware or CPU, but it has to go through guest operating system and then the VirtualBox, which is the hypervisor, and then it will go to the host operating system, and finally it will reach the hardware. So it has to go through all these additional layers, and because of that it will be slower compared to bare metal. There are some advancement made on this area recently. So for example, Intel introduced something called virtualization technology called VXT, and AMD also introduced something similar to run these kind of virtual machines on a hardware much more easily. So you can directly take some advantages from the hardware rather than going through all these software layers. But even then it is going to be slower compared to the bare metal hypervisor. So I don't want to go into the details of how a process running within a guest operating system manages to execute something in the hardware layer or access some IO devices, because you know that is going to be quite technical and detailed. Yeah, so because of that I'm just going to leave it here. But what I wanted to highlight is actually on this hardware, if you want to run different isolated operating systems or programs, then we can actually spin up, we can have many number of VirtualBox instances running on this particular hardware, on this particular host operating system. But each of those virtual machines is going to have its own guest operating system, which is going to be really heavy, right? So because running an operating system is not cheap, it is going to allocate some memory, and it is going to take up some CPUs and all those things. If our intention is just to run one of the application in a really isolated environment, I just want to run this application X in a isolated environment, so it won't have any impact because something changed in my host operating system, or some other application which needs some program which causes problem running this application. So if that is your requirement, you just need the isolation to run this application. So because your host operating system can have many applications, and each of those applications may have their own dependencies, and there might be conflicts between those dependencies. So you just need a way to isolate running this application 1 from application 2, and you just want to provide the dependencies for application 1. For example, application 1 might depend on X library, Y library, and Z library, and application 2 might depend on the same X library but different version. So let's call it X.2, and it depends on another library called B. So now if we try to run both of these on the same machine, we may need to deal with this version conflicts. So one way to avoid that is if we somehow isolate this application from this application within the same host operating system, so they won't see each other. Like, application 1 will not see application 2, and they have their own dependencies, and these dependencies won't conflict with the other applications dependencies. Then that is going to be the best way to get the maximum performance, right? Because we're not running the entire guest operating system. We're just going to run this application in an isolated environment. It can still directly talk to host operating system. So we don't need this additional layer of guest operating system and hypervisor and all those things. The applications will get most out of the hardware that we have. So container exactly solves this problem. So this is why we have container. Okay, so let's take a step back and understand container now. So I'm just going to draw another box like we have done so far, but this time we're just going to start with hardware as usual, and then we are going to have our operating system kernel. Then we can have applications like application 1, 2, so on and so forth, and also we'll have containers. I'm going to call it a C1 and another container C2. So these containers are exactly this isolation. This is not a complete operating system like how we have one for virtual machines. These are like a very simple process actually. So if you see the host operating system, host operating system will see container 1 as one simple process and container 2 as another simple process, and each of these containers won't have their own operating system. They may have some user space programs, but they won't have any kernel or anything like that on their own. And then in addition to that, it will have the program that that we want them to run. So let's say, for example, I want container 1 to run app 1 and container 2 to run app 2. Then those programs will also be running inside these containers. Now the advantage is these two containers will not be able to see each other because of the isolation that comes from one of the Unix concept or Linux concept called namespace. So I'm not going to go into that in detail in this video, but I'll do that in the next video. So namespace will provide the isolation that we need for this particular container. So this container will not be conflicting with another container. So basically using namespace we'll be able to create isolation boundary. So each of these container will run in its own kind of a container, so it can't see other containers or what is going on in the host operating system itself. And in addition to this, we also use another Linux concept called C groups or control groups. So this will actually help us to define how much hardware each of these containers can use, because just imagine that we don't have anything like C group, and this container takes all of the memory available and it takes all of the CPU available. Then it is not going to be good, right? Because your host operating system is running some applications also, so it needs some memory and other hardware to run. If this container takes everything, then it is going to create problem, right? So with the help of C group, we can limit how much hardware this particular container can use. So we can say this is the maximum memory you can use, this is the maximum CPU you can use, and that can be defined for each of these containers. So that is what the C group allows us to do. So with these two Linux concept, we have created these containers, and these containers are running just like a simple process. And if these containers the applications running within these containers want to make system calls, then they can just directly make those calls to host operating system. So there will be some filters. They can't do anything and everything. There are some filters, like they can't access things from the host operating system's application, or they can't power down the machine and stuff like that. So there are some limitations to what kind of system calls they are allowed to make, but they'll be able to do most of the things. Okay, so it is not going to be very restrictive, but it can't do everything. And in order to make the system call work, the container has to use user space programs which is compatible with the kernel operating system. Okay, so one of the advantages of Linux based kernel is that Linux based kernel is always backward compatible. So even if you are the kernel OS is very latest, but your container user space program is old library, it can still talk to the the host machine's kernel. But sometimes we may have problem if it is other way around. If the host kernel is very old and container's user space program is very latest and it is using some latest features, then we may have some problems. But that is very, very rare. Okay. Another problem that we may have is the CPU architecture. If your if your hardware is using ARM architecture, for example, then you can't just run a container which is compiled for x86. So this is another problem that we will face. So the container has to be built for the right CPU architecture. So if your host OS is ARM, then the container should also be ARM. So as you can see, because these containers are not running a full-blown operating system and they can directly talk to the host kernel, it is much more faster, and we don't allocate memory and other hardware to any other unnecessary programs here. These containers can directly use all of the allocated memory and CPU clocks for the application itself, rather than leaving some for the unnecessary guest operating systems. So this is why container is very, very popular. It provides this isolation that we have seen here, and also it provides very lightweight way to access your host operating system. That way we can take maximum advantages of the hardware available, and because of all these, this will be really fast. It will be very, very quick to spin up a container, and it will be also very quick to destroy a container compared to the virtual machine. Okay, so yeah, so that is basically what I wanted to cover in this video. I hope this is useful. Thank you.